Hello everybody, this is Sky Darmas, now from Germany. Recently I've been doing some calculations on neutron stars and white dwarfs, in particular the famous Tylor pulsar, which was used to prove that gravitational waves exist. Here is the equation that is used to calculate the orbit decay. And in SPD quantum gravity, G will be much higher. Instead of 6.67 something that we have for normal matter, for neutronium, which is the matter that neutron stars consist of, it's 8.017, and that's because in a neutron star there's a lot of negative binding energy, reducing the mass but not reducing the number of particles, so you have much more particles per unit mass than for ordinary materials. It's 15 to 20% binding energy. For black holes it's 30%. So then when we look at the mass, when we look at the GR mass, the general relativity mass of these neutron stars, we see that they are already below, not far below, but below the Chandrasekhar limit, which makes it somewhat doubtful that these are really neutron stars. And when we calculate their SPD mass, the true mass, we see that it's clearly below the Chandrasekhar limit, meaning that it's impossible that they are neutron stars. Also, if we assume that they are truly neutron stars, this term will be very high, and these will be lower, but we have this cubed here, so we get quite a big difference between SPD and general relativity here. This is 30 centimeters a year, this is 52 centimeters a year. This is too big of a difference. We know that the observed difference between is very, very small, the observed difference between general relativity and the actual orbit decay. And so when we assume that it's really a white dwarf pulsar, then everything adds up. And it's not on the board here because I wrote it in the paper. This whiteboard is from a few days earlier. So when we do that, we find a very tiny difference, and the difference that is observed is the ratio between the observed orbit decay and the orbit decay predicted by general relativity is a ratio of 0.9986, something like that, and my theory predicts pretty much the same. There's an agreement of 99.91%, and for general relativity it's only 99.86%, and no agreement within margins of error. So in my theory there's agreement within margins of error, while in general relativity there's none. Very similar case we have with perihelion precession, which I calculated 2 months earlier, perihelion precession of Mercury and Saturn, but that's a topic for another video. See you.